Hi there. After about 18 years of use, I thought it was about time that I just confirmed the fidelity of my speakers. Probably the easiest and possibly cheapest way of doing this is by using a noise source. A noise source can be divided into two categories: white noise and coloured. White noise has equal energy across all frequencies, whereas pink noise has equal energy per octave. This sounds more natural and is derived from filtering white noise at a rate of -3 dBV per octave. For example, 20 Hz to 40 Hz has a drop of -3 dB, as does 10 to 20 kHz. Other noise colours can be achieved. All of this is similar to the way light works, white being made up of all wavelengths, whilst an individual colour is specific, or a narrow group of wavelengths. White noise examples include, and this is not an exhaustive list, but it includes radio or television static, the stuff you see on a television screen, the old analog televisions, vacuum cleaner whirring fan, the hum of an air conditioner, strong hairdryer, steady running water, shushing and steady rain. Whereas pink noise examples include rain, waterfall, wind, river and ocean waves. It's alleged, and you have to find out about this yourself if you're interested, it's alleged that noise can help with tinnitus, the reduction by cancellation of other local noise sources, and relaxation. It has to be said as a warning, continuous loud noise can damage hearing. So be careful what you do. In audio, pink noise is a significant tool. My intended use regarding speakers can be tonally tested for driver and cabinet failings. Equalizer settings can be confirmed, and amplifiers can be checked for errors like a diagnostic tool. A noise source is used extensively by electronic synthesizers. However, be mindful that white noise can extend its full energy to maybe hundreds of kilohertz, so that could damage, depending on the volume settings and the loading of the amplifier, it could damage amplifiers and equipment. I'll go on now to the setup that will be testing my noise source design. This is a simple setup. Over the back there, top left, is a maintenance-free 12 volts DC battery, and in front of that is a digital oscilloscope set to 20 milliseconds and half a volt per division. Coming over to the right, you have naturally the breadboard containing the noise source, and finally at the bottom there is a switch which will select between pink noise and white noise, and it is currently set to white noise. Of course, you can't test / demonstrate a noise source without making a noise, so there will be noise throughout most of this recording. The noise source will be going through my amplifier and the speakers that I'm testing. I'll now unmute my amplifier so you can hear the noise itself. It sounds for all the world a bit like gas or air escaping, and perhaps a bit like listening to a motorway nearby. it's producing equal energy right the way up to the upper limits of the amplifier, and it's sounding to my ears a little thin, although I'm not quite certain what it sounds like to you, given the fact that of course this is uploaded to YouTube, processed by YouTube, and then you download this. I'm not quite confident as to what it actually sounds like to your ears. I'll now switch over to pink noise mode. Dynamically though, due to the emphasis of low frequencies, there will be an increase in volume, and I'll compensate that by dropping the volume of the amplifier. Having hooked up both the left and right channels of my auxiliary input of the power amplifier to the output of my noise source, and centering myself between the two speakers, I can clearly hear that both speakers are identical. I'm pleased to say that the bass drive units, the mid unit and the high frequency units are all producing good quality sound, albeit noise. I'll go on to first lifting the bass, then dropping the bass by the same amount, returning it to 0, and as far as I can tell, my microphone does not pick up greatly the bass notes of my speakers, so I'm not sure that that will be recorded. And then I'll go on to lifting the treble and then dropping the treble by the same amount and then returning it to 0. I'll go on to circuit design and description now. I'll firstly go through the circuit quickly, and then I'll follow that up with a more detailed look at this circuit, and then finally I'll end up with some observations. On the far left here we have the all-important noise source, a Zener diode, the noise of which enters a common emitter amplifier, which is gain controlled. The output of that drives, if selected into the pink noise mode, a 3 dB per octave filter. If the switch down here is selected to white noise, then this network is disconnected. The output of both white noise and pink noise goes into C6 and a 3 transistor output amplifier, finally emerging at C8 as the output. Now let's look at this in more detail. I'll move back over to the Zener diode noise source. It's critical. I personally have only a limited range of Zener diodes, and they're 1 watt Zener diodes. I started off with a low value and worked my way up, measuring the peak-to-peak amplitude of the noise that the Zener diode produce. And I found 2 facts about a Zener diode as a noise source. One is that it preferred a much lower current than you would probably think, and it really likes a higher supply voltage. I did in the first place choose a 9 volt supply, but I found Zener diodes lower than 7.5 volts to produce too small of an output voltage. So lifting it to 12 volts DC, I was able to produce a significant amplitude on this 7.5 volt Zener diode. It's worth bearing in mind that a Zener diode is a quantum device and therefore is subject to probability. R1 here is critical. If I were to use a 22K, I would get a drop in peak-to-peak value. If I move that to 15K, I would again get a reduced peak-to-peak value. It's optimized at 18K. The current flowing through this circuit is about 0.3 of a milliamp. So you can see how low this current is flowing through the Zener diode. Should you make this circuit, you could of course go through a range of Zener diodes. You could change the wattage to say 400 milliwatts, or try reducing the supply. But this voltage supply and Zener diode value I found to be the right choice. Moving on to the gain-controlled common emitter amplifier, the reason why it's gain-controlled, and this is set by the capacitor C2 and the switching between pink and white noise. When you switch in this 3 dB per octave network, it significantly reduces the amplitude going into the base of the output amplifier, and to compensate for that, I increase the gain of this first stage amplifier using these 2 resistors and that capacitor. When white noise is selected, the network is disconnected, and this point here goes open circuit. That enables the peak-to-peak voltage to rise to the full level, so therefore I don't need as much gain from this first stage amplifier. And now the network filter. Each stage here offers a -3 dB per octave, 1, 2 and 3. You would expect an RC filter to offer a -6 dB, but this is very carefully adjusted so that when one stage, the first stage, reaches -3 dB per octave, the next stage comes in and then produces a -3 dB per octave, and when that reaches -3 dB, it then moves into the next stage. And finally there is a capacitor here that cuts high frequency content. Whether it's pink noise or white noise, it all enters Q3 transistor here, which is an NPN common emitter amplifier with a collector load of a constant current of Q2, and that is a PNP. The stable voltage source is derived from a red LED that has a second purpose, and that is it's a power indicator. At the collector of the common emitter, back here, we enter a common collector of Q4, and that's an impedance converter to offer a low impedance drive to an output, so that effectively is an output device. The noise signal emerges through C8 and finally to the output here. This is an oscillogram of the white noise output mode, showing good signal symmetry and richness of harmonics. Moving on to the pink noise output now, showing the emphasis that's placed on low frequency content. So what do I think of this noisy project of mine? Brilliant, of course. No, only joking. It represents work in progress. This is partly due to the fiddling around with Zener diodes and through currents, etc., which finally ended up with a Zener diode configuration that was very reliable, as this is now. You can switch it on and off, the supply on and off many times, and every time the noise signal is generated. So due to that optimization, the output ended up twice as much as I would have liked it to be. So for my hi-fi amplifier to be compatible with this, I had to put a series resistor, a 4K7 resistor, in series with C8 on the output. The noise signal was being clipped. So other than that, I would also like to balance the output signal level better between the pink noise production and white noise production, so that they are fairly close in amplitude, peak to peak amplitude. So other than these amplitude issues, it's working really reliable and it produces a good noise signal. This is calling for an update, which I'll do shortly.